Welcome everyone, and our guest and speaker today tells me that when he was in school, he was kind of undecided between linguistics and physics. So I guess it was unfortunate for linguistics that he became one of the leading experts on the dynamics of galaxies in general and the Milky Way in particular. So let me not take away more of any of his time by reciting his CV, which you can look up, and it's very long. And what's your website again?
Somewhere.
It's somewhere. So just search for Eugene Vasiliev, and you'll find lots of you'll find more material than we can summarize right now. So please welcome Eugene Vasiliev.
Thank you. That made me think maybe I should switch to linguistics when I retire after all. We'll see how it goes. Okay, thanks for coming here. I'm happy to be here in this audience again. In Zurich about 5 years ago, talking about the progress in the Milky Way studies coming from the Gaia satellite. We have obviously even more progress since those days, but I'll be in this talk mostly focusing on a particular topic in the galactic dynamics in the Milky Way and the dynamics of the local group, and that is the interaction between our galaxy and its largest neighbor, the Large Magellanic Cloud. To start with, this is a standard picture in the all Milky Way related studies. This is the Gaia sky, and this speck on the sky here, circled, of course, is the Magellanic Cloud, the Large Magellanic Cloud, and next to it is the Small Magellanic Cloud. And these are very prominent features on the sky. And let me start by recapping their properties. The Milky Way, of course, is the galaxy that we live in. Its mass is about 10 to 12 solar masses, and there are other properties that are summarized here in this table. And by comparison, LMC is a few times smaller, maybe between 5 and 10 times smaller by all parameters. Stellar mass, the total mass, the radius, and the various other properties. It looks also a bit less regular. I think historically, it was always considered to be like a regular galaxy. But when you look at its appearance in the kinematics, actually, it looks more like a disk galaxy, but a puffy disk galaxy, not like a Milky Way. So by all means, the galaxies are not kind of equal in comparison. And to illustrate this, I put this picture here, which is my Swiss connection, because most of these protagonists here have some connection to Zurich. Lenin was living here before he dropped his political studies and went to practical applications. And Giacometti, of course, is one of the Swiss national artists. And what are the charges that I bring against LMC? I portrayed it as a villain, and what do I accuse it in? First of all, this is kind of the summary of my talk. What I'm going to talk about the positive and negative effects of the LMC on the Milky Way system and the life of galactic dynamicists. Let's put it this way. The positive effect is that LMC brings some material so we can study these things in more detail. Most other things are negative in the sense that they make our lives more complicated, but that also makes it more interesting. I will actually start not with the first one, but with the other factors, and that is the effect of the LMC on stellar streams. And to introduce the concept, stellar streams are structures arising from the tidal disruption of star clusters or dwarf galaxies. And actually, I maybe even play a movie to illustrate it first. So here is an illustration of like a very, very theoretical concept. The galaxy is represented by point mass, and this cluster of the star cluster or satellite galaxy is a collection of particles. Here is just a zoom in on the cluster. If this guy is orbiting the central galaxy, of course, it is embedded in the tidal field. And these isocontours here show the contours of the effective potential. And much like in the dynamics of Earth, Moon, Sun system or many other three-body systems, we have Lagrange points here through which the debris can escape if they have sufficiently high velocity. So this is the concept of tidal stripping. And as this satellite will be orbiting for a long time, it eventually will lose most of its mass and form tails that could be long on the sky. The satellite itself could be completely disrupted, or it would stay there. Whatever the fate of it is, the debris are a prominent feature on the sky. And the map in the top left corner shows the sky as we have seen it about 20 years ago, with the advent of some of the first large-scale surveys of the sky, in this case, the SDXS survey. And highlighted features include one of the most prominent streams. The most prominent stream is the Sagittarius stream. It's a greenish, reddish one. And then there are a couple of other streaks on the sky that look thinner, but they also are produced by disrupted or partially disrupted satellites or star clusters. Some streams are very thick, like Sagittarius stream. Some of them are thinner. This one is produced by one of the globular clusters in the Milky Way. And by now, we have more than 100 streams crisscrossing the whole sky. And that the amount of data has been assembled largely in the last few years, and in a large part thanks to God, because it's very easy, much more easy to detect streams when you have velocities of stars than when you just look on the sky. But my talk is not about the streams today. It's the effect of the LMC on the streams that is important here. And one of the first things where this was noticed was the so-called orphan Chenab stream. It is called so because orphan is because no one was able to find the progenitor. Most likely it has been disrupted fully. Chenab is the other part of the stream that was originally thought to be an independent one. Then it was linked to the orphan one, whatever the story is. The orphan Chenab stream is a very long stream on the sky. It spans more than half of the big great circle. And the interesting thing is that this stream displays a very interesting feature that is the misalignment between the direction of the stream track and the direction of the stellar motions. Because stars, when they leave the progenitor, they travel mostly along the same orbit as the progenitor. So if you look at their velocities, they should line up, but they don't. And this misalignment expressed here just via arrows. Here is the same thing expressed in terms of, well, you see that the stream is it's not a straight line, it's distorted, and the wiggles here are a result of a close passage of the LMC. This study has been already 5 years old, and it also had an illustration, which I think would help to understand what happens here. So this is the n-body simulation of a disrupting satellite, whereas the black points show the observed data, but this simulation would eventually produce something that should look like observed data. But as you see, this satellite happily keeps disrupting. At some point, the LMC comes from behind the corner and passes not too far from the trailing arm of this stream. And if you look at this configuration in 3 dimensions, it appears that it has deflected stars in the trailing arm. So they left the original orbital plane, and they now travel with the velocity that is directed a bit towards the LMC. So now it's not directed along the orbital plane of the stream itself. That's why we had this misalignment. So that was the first stream that was found to have such misalignment. But yeah. Yes, more or less, because the orbit of the stream could be reconstructed with reasonable level of precision if you know the galactic potential or make plausible guesses about the galactic potential. And the encounter happened relatively recently. I forgot to mention at the very beginning, put it on the slide, but I forgot to say it loud, that the LMC is currently just past the pericenter of its orbit at a distance of about 50 kiloparsec, compared to the distance of 8 kiloparsec from the sun to galactic center. So it's quite far from us, quite far from the galactic center, but it's near the pericenter. And this stream in particular was, it's not very close one. I think it's about 15 kiloparsec away. So the LMC was passing not too far from it at a distance of, I forgot, maybe somewhere between 10, 15 kiloparsec or so. And again, not too long time ago. So maybe 100 years ago. And in fact, as I said, this is not the only stream that displays this kind of feature. There are a couple of other streams, which I think this plot here answers your question a little bit. Although it doesn't display the time, it displays the distance of the closest approach for several streams in the southern hemisphere. So the orphan Chenab is this one, long feature because, well, it's not a single point, it's a collection of points. So in the closest part, it was within 15 kiloparsec, as I said, so that was a plausible guess. There are other streams that have even closer passages to the LMC, but with higher relative velocities. And of course, the dynamical effect is the combination of the relative distance and relative velocity. So the strength of the effects are parameterized by these isolines. Anyway, so from the perturbations on the stream, you could in principle measure the LMC mass because, well, the more massive it is, the larger would be this kind of deflection. And that's what this study here did for several of the streams. And they all indicate those streams that do have significant perturbations. If you model them, having the LMC mass as a free parameter, they converge to more or less the same range, which is between 10 to 11 and 2 times 10 to 11 solar masses, more or less. And with the orphan chain upstream, because it's so long, you can actually probe the entire mass distribution of the LMC to some extent, because different parts of the stream get perturbed differently. And you can probe the enclosed mass as a function of radius. So this is the follow-up study to this 2019 paper for the same stream with more extended data. They were plotting constraining the mass distribution of the LMC with a absolutely exquisite precision to my eye. It's like in the best place where they can do it, where most of the data is located. It's like 15% or maybe 20% or so. So the streams, they're very sensitive probes by virtue of being dynamically cold systems. They can also be very easily perturbed, and you can use them as a very fine probes of the perturbations from the LMC. That is interesting, but this is not the only effect of the LMC on the streams. The largest feature on the sky, apart from the Milky Way itself, is the so-called Sagittarius stream. And it has been discovered also about 25 years ago with the advent of first large-scale surveys on the sky. And this stream is produced by the galaxy that was also named Sagittarius Galaxy. The galaxy is sitting behind the galactic center at a distance roughly 3 times further than the galactic center from us, so 25, 27 kiloparsec. And it's sitting more or less just a little bit below the galactic plane. That's why the galaxy itself was actually undetected for a very long time, even though it's one of the most prominent, well, it's one of the largest satellites of the Milky Way. But unlike the Magellanic Clouds, it was hidden behind the bulge. But with the infrared data, with the velocity data, it was detected. Then the stream was detected, which again spans a large part of the sky, more than 360 degrees on the sky. And it so happened that both Sagittarius Galaxy and the LMC are near their respective pericenters. Sagittarius is twice closer. It's 3 times closer. Its pericenter is about 16 kiloparsec from the Milky Way. LMC is at 50. And their orbits are perpendicular to each other and also perpendicular to the disk plane. So this is the disk plane. The LMC goes this direction. Sagittarius goes in this direction. But in the past, their orbits were, again, not too far from each other. So they crossed here, not only in space, but also in time. So the LMC went from here to here. Sagittarius went from here upwards. And this stream, because it's so prominent, it has been studied, again, in exquisite detail. I did a study of the stream some years ago. And the data on the stream are very extensive, as I said, but I don't want to spend too much time on it, just to focus on 2 particular features. So these are the data in all 6 dimensions, the 2 components of proper motion on the sky, the distances that are measured for some classes of stars, line of sight velocities, and this is the illustration of the stream viewed side on. So the galactic plane is horizontal, the sun is here, this is the galactic center, and this progenitor, the Sagittarius Galaxy, which is still alive, is sitting just below the galactic plane. The trailing arm and the leading arm are both very clearly visible on the sky. And what we see here is the same kind of misalignment between the direction of motion of stars in the stream and the stream track itself. Maybe not very clearly seen, but the arrows point not in the same direction as the stream, and the misalignment expressed in terms of the difference between the gradient of the stream track and the direction of the proper motion vector is here. So this offset here basically tells you the angle of the misalignment. In this plot, the progenitor sits at the center. This part is the trailing arm, the one that is in the southern hemisphere and the closest one to the Sagittarius stream. And this leading arm is in the northern hemisphere. But the misalignment actually is stronger in the leading arm. And that is quite interesting because the LMC was passing near the Sagittarius, but it was passing in the southern hemisphere, closer to the trailing arm. So why would it perturb things in the leading arm? The answer is that the interaction between the Milky Way and LMC is more complicated than just a direct perturbation from a moving body to the orbits of stars in the stream. The perturbation, this is the important one, and that's the thing that you have seen in the previous plots with the other streams, but it's not the whole story. And to understand what happens here, let me first show you how this stream could be modeled using simulations of a disrupting galaxy. If we ignore the LMC, my best fit models, which were very, very extensively studied with the parameter space for the Milky Way potential was quite wide, trying to vary the properties of the progenitor, various other things. If I flip back and forth, the match between the models and the data is reasonably good, but there are two areas where they don't match. First of all, there is no misalignment. If there is no LMC, there is no misalignment between the stream track and the proper motion. Unlike in the data, this part in the models, there is complete coincidence in the direction of motion of stars. And second, also in the leading arm of the Sagittarius stream, I could not fit the orbit that well. The leading arm always gets a bit further away. However, if I include the LMC with plausible orbit in these simulations, then both things actually get better. So the misalignment becomes in place. Again, it is more prominent in the northern hemisphere, not in the south. And the leading arm, which is in the northern hemisphere, also gets better positions. So as I said, the puzzle here is not so much why we get the misalignment, but why the misalignment is in the wrong part of the sky. And to answer this, we have to consider the overall perturbations induced by the LMC in the entire Milky Way, not just in its immediate vicinity. But before going there, let me talk about the immediate vicinity first. The immediate vicinity of the LMC, or basically any other gravitating body, is where you have the effect of dynamical friction. Let me play another movie here to illustrate it. So if you have a massive object moving through a sea of stars, if you sit in the reference frame associated with this massive object, you will see that stars basically move as a headwind. So you experience them as a headwind, and their orbits are deflected by your massive object. So they will become more concentrated behind it. And you could convince yourself perhaps that there is a bit of overdensity here behind this object than elsewhere. So this overdensity naturally creates a gravitational pull and slows down the moving object. So that's the essence of dynamical friction phenomenon. And for the LMC, it would be making its orbit tighter, but also it will create this overdensity behind the trajectory of the LMC. That's the expectation. Do we see it? Yes. There are detections of stars in the past orbit so in the direction of the sky where the LMC was in the past. On these plots here, it would be roughly in this region. So where the LMC was between 200–300 megayears ago. Because this wake comes with some time lag, we don't expect it to see just behind the LMC, but it should be stretched along its past orbit. So there is this local effect again. It's more or less the same kind of effect as the deflection of the streams, because it's naturally the deflection of stars, and then now they concentrate behind the orbit of the LMC. But again, this is not the only thing. And the second interesting effect, which is less obvious, is the global distortion of the Milky Way halo in total. Now, let me play you another movie to hopefully illustrate this concept better. So here is my simulation of the Milky Way LMC system. The Milky Way is portrayed by red contours for the density, and the arrows show the velocities of stars. And green is the LMC that comes from behind the corner. And so as it goes here towards the LMC, towards the Milky Way, coming closer to its pericenter, what you see is that the directions of stars or particles in the vicinity of the LMC, they get deflected. So they form the same kind of density wake behind the LMC itself. This bulging of the contours of the density basically tells you the story that there is enhancement of density along the past orbit of the LMC, the density wake. But also what you could notice is that as time goes on, the LMC comes in the south, and now that's where it is right now. the Milky Way has shifted because both galaxies are, well, the LMC is not a test particle. Its mass is between 5 and 10 times smaller than the Milky Way, but both galaxies orbit each other more or less like a binary system. Very unequal mass binary, but still binary. So the LMC goes around the common center of mass. Milky Way also goes in the opposite sense around the common center of mass. And now the velocity of the LMC is pointing this way. The velocity of the Milky Way is pointing the opposite sense. But what you could see from these arrows is that this velocity is not uniform across the sky. And the thing is that the Milky Way is not moving as a rigid body. It is internally distorted. The parts of the Milky Way that are closer to its center, the dynamical times here are short enough so that the perturbation from the LMC comes more or less as an adiabatic thing, or in other words, the inner part of the Milky Way moves coherently as a more or less like a rigid body towards the LMC. Or rather, as you could see, it's moving towards where the LMC was shortly in the past, some time ago. But by contrast, the stars in the far outer parts of the Milky Way, their dynamical times are much longer, so they don't have enough time to respond to the LMC as quickly. And that's also because they're much further away from the LMC. So the impact of the LMC on the more distant stars in the Milky Way halo is smaller. And what happens now is that these stars get less accelerated with respect to the original reference frame than the Milky Way center. Now, if you are putting ourselves, this is the same plot, but with the axis flipped, sorry for that. Now, if you put ourselves in a reference frame that is associated with the Milky Way center, because that's where we sit as observers in the Milky Way disk, which is on the scale is roughly here. It's a small structure compared to the distance to the LMC. This whole thing is moving down. So if you are sitting in this reference frame, you have to subtract the velocity, downward velocity of the Milky Way's center. And what we end up with is that everything else starts to move up. And that is the effect that people call variously the global response or dipolar perturbation, polarization pattern. The essence of this effect is, once again, is that the Milky Way is not a rigid body, it's being distorted. And the inner part of the Milky Way moves down, the outer part lags behind, and it appears to be moving up in the reference frame of the observers in the inner part of the Milky Way. So you see it in the velocity, and you also see it in the position, because the inner part again shifted down, and the outer part stayed where it was. So now the stars that were originally, let's say, at 100 kiloparsec, now they find themselves at 120 kiloparsec. But the density is still as it was there at 100 kiloparsec now. So now if you look up, you would see that the density of stars at large distances is higher than you would expect. And conversely, in the southern hemisphere, it's lower at the same distance. So you'll have this enhancement of density in the upper part of the Milky Way and lower density in the southern part. And that is on top of the local wake from the LMC caused by the dynamical friction. So the overall response of the Milky Way halo has these two components: the local transient wake, the Chandrasekhar dynamical friction behind the LMC on its past orbit, and the global collective response, which is a more like a dipolar polarization pattern, and it's in the opposite sense. It's more stronger, it's enhancement of the density in the north, where the LMC never had been, but it's caused by the inner part of the Milky Way moving with respect to this outer part. So all of this is a prediction of various numerical simulations and analytic or semi-analytic theories. How does it fare against the observations? This has been possible only very recently. And the observations that we could hope to look at are the velocities, line-set velocities of stars in the Milky Way halo, and the perturbations in the density, because as I said, there are both the consequence of the same effect, especially in the line-set velocities, which are perhaps easier to measure spectroscopically than the tangential velocities measured by proper motions. In the line-set velocities, you should see that if you look up in the northern hemisphere, you should see things moving away from you. And these line-set velocities should have this dipolar pattern. In the northern hemisphere, especially at large distances beyond 60 or so kiloparsec, the stars in the north should be moving with positive velocity. In the south, they would be moving mostly with negative velocities. And in the density, if you look on the sky maps of the density, this is the top row here, you would see, or you expect to see the perturbations, enhancement of density along the past orbit of the LMC. This is the local wake. And then on the larger scales, again, the same dipolar pattern, where this northern part will have an enhancement of density, the southern part will have a reduced density. So this, again, is the prediction from various simulations. And observationally, we have at least qualitative agreement with these predictions. So in the velocities, which are somewhat easier to measure, the velocity have the amplitude of perturbation north-south asymmetry at the level of between 25 and 50 kilometers per second, depending on the tracers that you're using, whether they're stars in the outer halo of our galaxy, or satellite galaxies, or globular clusters, again in the outer part. They mostly tell the same story. And this velocity offset is comparable with what the models predict, although there are some details here which, so there is not a perfect agreement, there is still work to do. And in the density, again, this is the sky map of the density. Tentatively, there is an enhancement of density in the northern hemisphere and reduction in the southern, and in addition, the enhancement again along the past orbit of the LMC due to the dynamic friction-induced wake. Although for the density, it's even harder to measure it reliably because unlike velocities, the densities are affected by your survey design. If you look mostly in the north, of course, you'll see things in the north, but you have no way to compare whether it's more density or less density. In addition, there are structures in the sky, in particular the Sagittarius stream itself, which is a very prominent feature, and it has to be excluded in order to study the density enhancement. So there have been contested findings. Some groups do not confirm this. Some groups find that there is like much higher density than you would expect. So this is still an open question. But I think it's quite plausible that, nevertheless, that we will eventually find confirmations of this bipolar polarization pattern in the density of the tracers in the outer halos. So this is why the Sagittarius stream, going back to this story, why it was most affected in the north. Basically, this northern part of the Sagittarius stream was moving away from the Milky Way, and it was moving not in the direction, in the same direction that the stream itself is moving. So it so happened that the perturbations in the velocity were most prominent in the north, and this is not where the LMC itself was. So they are more like the manifestation of this global perturbation rather than the local deflection. Okay, so the LMC is certainly making a lot of noise in the outer galaxy. So how does it affect our ability to measure the mass of the Milky Way, or mass distribution of the Milky Way? In general, there are several methods for doing this. Most of them rely on the assumption of a steady state or equilibrium, except the methods based on stellar streams, which I already described to some extent. Stellar streams are structures that are manifestly time-dependent. They start forming, they stretch along the orbit, and their orbits could be, fitting the stream orbits, could be used as a way to measure the potential of the Milky Way. So the studies that I mentioned already, the Orpington upstream and the Sagittarius stream, they both use the models to constrain not only the Milky Way, not only the LMC mass, but also the Milky Way mass. I will later show how these constraints fare against each other. But most other classical dynamical modeling methods invoke the assumption that the galaxy has been around for a long time, and tracers in the galaxy have had time to reach an equilibrium state. And obviously, this assumption now is called into question once the LMC comes and perturbs them, especially in the outer part of the galaxy. And the question is, how much perturbation would you expect, and whether it's possible to compensate for it in some way. The first question has been answered again by Erkel et al. In 2019-2020, when they looked at the mock data from their n-body simulation of the LMC interacting with the Milky Way. And these mock data were produced from the perturbed galaxy. And when they applied classical dynamical modeling methods, in this case, Jeans equations, to this mock data set, they find that you get a biased inference about the Milky Way's mass. And this bias was, so this is the true mass shown by the dashed line, and that's what they measure for different masses of the LMC. So they always, the answer from the model always comes up higher than the true answer. And this bias is at the level of 10–20%. So it's stronger, obviously, for the larger LMC masses. And perhaps it's not easy, not so difficult to see why, because basically the LMC induces more velocities, so higher velocities of tracers, which in the language of dynamical modeling means that you expect more mass there. I think it's not the only reason, but it's at least the most obvious reason why the mass comes up higher. The question is now whether we can somehow undo this perturbation or maybe adapt our methods to compensate or take into account the perturbation in a better way than just fitting it and then subtracting 15 or 20%. And that was the work that I've done with the summer student Lilia Correa Magnus a couple of years ago. And this work is based on a relatively small modification of this above scenario. So the assumption here would be that before the LMC came in, the Milky Way was still in relatively good equilibrium, which is, I think, not a bad assumption, because the previous interesting things in the Milky Way history happened many giga-years ago. So it's probably safe to assume that the LMC was just a recent perturbation, and before then the Milky Way was okay. And depending on the Milky Way potential, of course, the past orbit of the LMC would be different, but that's the whole point of the story. We can assume different properties of the Milky Way potential. Then we can reconstruct the past orbit of the LMC in each of these choices of potential. And then we can look at how the orbits of tracers, stars or global clusters in our case, how they would be perturbed by the LMC, and fitting the present day positions which have been perturbed by assuming the potential that has been there before the LMC came 2-3 giga-years ago. So in some sense, it's kind of rewinding the present day orbits back into the past until the time that they were not perturbed, but it's done in the opposite sense because forward modeling is conceptually better than backward integration, so to say. And this method is a relatively simple extension. Once again, we take the positions of tracers, we perturb them by the arriving LMC, and then we find which of them are, which of the Milky Way mass distributions, which of the Milky Way potentials are best consistent with the observed distribution of positions and velocities of these tracers. And what we find is, yeah, we confirm that the perturbation of the LMC causes an upward bias of the Milky Way mass estimates if you ignore it. If you don't ignore it, if you take it into account, we can actually measure or constrain the Milky Way mass pretty well, and constrain the LMC mass as well. And the constraints I will show you a bit later. What I would like to show now are how these tracers are actually perturbed themselves, because for tracers, we are using mostly the kinematics of satellite galaxies. In total, there are about 50, 60 satellite galaxies in the Milky Way system, as we know now. This census is probably not complete, but this is present day. And many of them their orbits have been perturbed by the LMC to a significant degree. So here, this is showing just a few of some of the galaxies with the orbits reconstructed in the past. Each panel shows the galactocentric distance of a given galaxy, and there is not just the one line, but there are many, many possible lines which sample over the uncertainties of the mass distribution in the Milky Way and over the measurements of the position and velocity of the galaxy in the past. And what you could see, for example, if you take this galaxy, Leo 1, this is one of the least bound galaxies in the Milky Way system. And so it is traveling with high velocity away from the Milky Way. So it certainly had one pericenter passage before. It's not just an interloper. It probably has been in the Milky Way system for a while. But its current position is at 250 kiloparsec, roughly at the virial radius of the Milky Way, and its velocity is very high. So in order for this galaxy to be bound, the Milky Way mass needs to be pretty large. And that has been always one of the straws in the eye of the Milky Way mass estimates, because it's not biasing, it tells you that the Milky Way mass should really have been high in order for Leo 1 to be bound. However, what you could see is by comparing the blue lines, which are the past trajectories without the LMC, with the red lines, which are the past trajectories including the perturbation of the LMC, the red lines, the red orbits, are more bound. So the apocenter of the blue orbit would be somewhere here, the red one would be here. So the red orbit, including the LMC perturbation, ends up being more bound. And you could also see that by these green lines, which show the energy evolution of the orbit as a function of time. So it was more or less constant, and then recently the energy became higher. So what happened is that the perturbation from the LMC caused its orbit to become less bound just very recently. But in the past, it was not so unusual in a sense. There are examples of the opposite sense, like Draco, for example, is another galaxy which has the opposite trend in energy. It used to be less bound before the LMC arrived, and now it became more bound. And there are galaxies which have been little affected, like this, for example, has little changes in energy. And of course, there are galaxies for which the past orbit will be completely different if you ignore the LMC, like SMC, it's the most massive satellite. If you include the LMC, it will travel along with its orbit in the past. If you don't include it, it will just go in completely separate ways. And these LMC satellites could be detected by looking at, rewinding the orbits of the satellites in the past and seeing how close they stay to the LMC itself. And this census of satellites, I'll again later show that we have about a dozen, maybe 10, 11 satellites of the LMC as of now. Now back to the mass estimates. Here is the compilation of studies from recent years. Obviously, this work has been going on for many years, but here I'm showing only the compilation of studies in closed mass of the Milky Way as a function of radius from different tracers and different methods, Jeans equations, distribution function models, and so on. And they more or less paint a coherent story. The enclosed mass keeps growing. The virial radius of the Milky Way would be somewhere here, and the virial mass is about 10 to the 12 solar masses, as I already mentioned. And the three studies that I did include the LMC in their analysis are shown by these bands, colored bands. Two of them are based on the streams, the Orphan and Sagittarius stream. They look very, very similar. So the blue and the green lines, the more confidence intervals more or less coincide. The red line shows the inference from the satellites, the rewinding scheme that I just described, which is slightly higher, but it's still consistent with it. Other studies did not consider the LMC perturbation, but it seems that actually this 10% bias is not so obvious given the scatter of these data points. And the studies that included the LMC, they also could measure the mass of the LMC. And again, different tracers and different methods paint more or less consistent picture that the mass is somewhere between 1 and 2 times 10 to 11 solar masses. So again, between 5 and 10 times smaller than the Milky Way itself. The interesting twist in the story is that these are the data in the outer part of the galaxy, roughly beyond 20 kiloparsec and up to a virial radius. If you look at the kinematics of stars in the inner part of the Milky Way, or rather in the outer part of the disk, but within 20, 30 kiloparsec. These are all methods based on the Jeans equations and based on the kinematics of stars in the galactic disk. And it's shown in a different way, not as an enclosed mass, but rather as the circular velocity as a function of radius, which is the enclosed mass. Yes.
Sorry, just clarification. So the mass of the LMC is this. This is not. So this is the current mass, excluding the stuff that has to come down.
Yes. 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 I'll come to that point later. Yes. Thanks. Yeah. So one thing that I wanted to mention here is that studies that look at the inner part of the Milky Way, or rather outer part of the disk, they find consistently, different groups find that there is a drop in the galactic rotation curve beyond 20 or so kiloparsec. And that drop is, if you try to construct a model that fits these data, it would completely not fit the data further out. So the mass of the Milky Way would basically had to end up here and stop growing, but it would not explain the data in the outer parts. So the line that goes through these other data points is shown here by this fiducial model that is dashed line, and there is some sort of disagreement. That's again to illustrate that despite great progress in the studies of the Milky Way potential and the mass distribution that we had in the recent years, there are still some questions that are not completely clear. And one of the possible reasons why there is a discrepancy in these measurements in the disk is that the disk itself is being perturbed by the LMC. We know that there is a warp in the Milky Way's disk at the distances beyond 15, 20 kiloparsec. And this warp could be in principle induced by the LMC, or at least partially caused by the LMC, because it passes through the disk, things get perturbed. Interesting thing is that, so this is the perturbation in the mean z coordinate and the velocity. The interesting thing is that in the future, the Milky Way disk will be even more strongly perturbed by the LMC when it keeps orbiting the Milky Way, and eventually will also get tidally disrupted. But in the future, the disk, it will not be destroyed, but it will be significantly puffed up in the few giga-years from now. So this perturbation from the LMC, I think it needs to be accounted for, but it seems that it also cannot explain this discrepancy altogether. So there is still questions that are open. Another thing that might be interesting for this audience is that LMC, even though it is currently at 50 kiloparsec, but its halo, dark matter halo, extends quite far. And the debris, in particular tidally stripped debris from the LMC's halo, might be traveling through the solar neighborhood, and they will travel with very high velocities. So if you look at the distribution of velocities of dark matter in the solar neighborhood, obviously it declines with the velocity, but the very tail of this distribution might be populated mostly by the LMC debris. So there are several studies that looked into it and concluded that if your detector is very sensitive to the high velocity tail, then you might be actually measuring the LMC debris, not so much the Milky Way distribution, which is interesting. If you ever have these detections, I think it would be a good place to compare the predictions for the model. Now, the last part that I want to talk about is what about the past trajectory of the LMC? After all, I was telling you that the LMC is currently just past its pericenter. Was it for the first time or not? The common lore is that, yes, it has been on the first pericenter passage, and the arguments in favor of this scenario are numerous, but one of them is that it basically flies with very high velocity. Its velocity with respect to the Milky Way is almost at the escape velocity at a given range distance, but not quite, but it has suffered from dynamical friction a little bit, so its velocity is slower than the escape velocity, but not by much. And different studies have looked into the past orbit of the LMC by taking the present day position velocity and trying to integrate it into the past. And of course, the result depends on the Milky Way mass. So here I'm showing you the examples of possible past orbits. Each of them is not a single orbit, but has an uncertainty based on the uncertainty of the present day velocity measurements of the LMC. But three different curves show the uncertainty or scatter between different adopted Milky Way mass models. And they differ only by 10% in each sense. So last year, I was writing a review of the Milky Way LMC interaction, more or less along the lines that I was talking about here. And I repeated the statement from the literature that the Milky Way, the LMC likely passed the Milky Way for the first time. And then I was thinking, is it really true? Can we exclude these alternative scenarios entirely? And after some time, I came to the conclusion that actually, no, there might be an alternative scenario where the LMC had more than 1% passage in the past. So if you look at these orbits, some of them at least, they turn back. So in the past, they might have another passage. And if you do this experiment for a longer time in the past, not for 5, but for 10 gigayears in the past, you see that there are trajectories that might be coming to the Milky Way sometime in between 5 and 10 gigayears ago, bouncing back beyond the virial radius, having an apocenter at 300-400 kiloparsec, and then coming back here. This is the present time, and coming back at much closer than before. So this alternative scenario of the second passage of the LMC depends mainly on the Milky Way mass. If you change it by 10%, the orbital period changes by almost 30%. If you change it by another 10%, you can make it unbound, or you can make a first passage rather than second passage. But this 10% uncertainty is more or less what we had from these plots. You see that the scatter here is at least at the level of 10%, maybe 20% is probably more realistic. So it's certainly not excluded. We should measure the Milky Way mass better, and that will tell us whether the LMC might have had another pericenter passage before or not.
That's when if you had a second pericenter, then the tidal mass of your system.
It will be different, yes, but not that different after all, because if you look at this plot, the second or the previous pericenter passage would be at a distance of 100 kiloparsec, not at 50. And this difference between 100 and 50 is the dynamical friction-induced loss of energy in the orbit. And at 100 kiloparsec, when the LMC was also more massive in the past, its tidal radius would have been at least 30-40 kiloparsec. So it would have retained most of the satellites that it came with. At least all the guys that are currently orbiting the LMC would have no problems surviving this previous pericenter passage, which is an interesting story. But the more interesting aspect is that there might be guys who actually were coming with LMC in the past and did not survive this pericenter passage, or they were rather stripped from it. And to look at this, having these embodied simulations at hand, I could easily find the analogs of the various satellites in the Milky Way system, looking at their present-day position velocities and tracing their orbits in the past in the simulation to find whether they came from the LMC system or from the Milky Way system. And this is the illustration for a couple of satellite galaxies, where, again, what is plotted here is the time evolution of the galactocentric distance for a few galaxies, and comparing it to the distance of the LMC itself in one of these scenarios where it had the pericenter passage 7 gigayears ago. The LMC is shown by this dashed line. And the galaxies like SMC, which have been orbiting the LMC likely since forever, they came with LMC. They always stayed close to its orbit, bounced back, and then now they come again. Some other galaxies, like this one, it's one of the ultra-faint galaxies, its uncertainty of the present deposition velocity is high enough that both scenarios could not be excluded. It might be coming with the LMC system, always staying close to it, or it might be orbiting the Milky Way. So roughly half-half. Actually, maybe for Bruce one, it's a 1/3 or so probability that it came with LMC, and the rest is not. But there are also galaxies like this one, which came with LMC, might have come with LMC, and then on the first pericenter passage, they got stripped, and now they orbit the Milky Way completely separately. Leo 1, Leo 2, and various other satellite galaxies. Let me show you another movie which illustrates how that scenario could play out. I'm not sure if you could see these small colored dots here, but basically this blue thing is now the Milky Way. The orange one is the LMC coming in. And there are a few galaxies indicated here by dots, which in this case, they were all assumed to come from the LMC system. And when the first pericenter passage happens, you see that some of them already get stripped. This one got a bit ahead. It went on its own orbit. Then other guys also got stripped. And the only one that remained faithful to the LMC was the SMC. So it keeps orbiting it for a while. But the other guys, they went their separate ways. And now the LMC comes back for the second time. And this is the present day positions and velocities of these galaxies, which are completely consistent with the observations. But in this scenario, all of these guys would have come on the first passage of the LMC and were stripped. It's one possibility, one realization. Again, for the list of galaxies listed here, the ones shown by the blue probability bars, which are all close to 100%, these are the present-day satellites of the LMC, which stay gravitationally bound even now. And the red ones are the probability of each of the other galaxies to be coming with LMC on the first passage and being stripped, and now being orbiting the Milky Way separately from the LMC itself. So none of them has a very high probability. The highest is maybe 2/3 or something, but quite a few of them have a probability around 0.5. So half-half.
I have a very basic question. Like in this scenario and other scenario, is LMC at some point going to merge with Milky Way? Or?
It will merge in the future, yes. If you wait for another few gigayears, it will obviously bounce back again, but on a smaller and smaller orbits, until eventually it will get tidally disrupted and deposit its mass in the Milky Way halo.
Because I read somewhere that Andromeda is going to merge with in 5 gigayears. But
yes.
Here, even the closest passage, even though it's got 10 or 8 gigayears, it's still a long way to merge. Is it because it's centric orbit?
No, Andromeda is currently much further away. So Andromeda is currently at almost 800 kiloparsecs from the Milky Way. It's moving towards it, but it will take a few gigayears before it arrives. And then again, it bounces back, and the merger with Andromeda will be completed, I don't know, maybe 10 gigayears from now. But the first pericenter passage of Andromeda will be in 5, maybe 3-4 gigayears from now. By this time, the merger with LMC probably will be nearly complete. So there are still things happening one after another, but not so much different in time. So going back to this analysis, what this illustrates is that for some of the classical satellites of the Milky Way, it is quite possible that they came from the LMC system. And interestingly enough, how this could be a proven or disproven observation. The thing is that in the Milky Way, as well as in some other galaxies, we have a notable anisotropy on the distribution of satellite galaxies, both on the sky and in the direction of their orbits. On the sky, it has been known for a while, because if you just look at the positions of the galaxies, they line up on some sort of plane. Not all, but a significant fraction of galaxies lie on the so-called giant plane of satellites, or vast plane of satellites. The disk of the Milky Way in these coordinates, again, is horizontal, and this plane is more or less perpendicular to the galactic disk. And even more interestingly, it's not just a spatial coincidence, but they also many of these galaxies tend to have velocities that are in this orbital plane. So the direction of angular momentum of the galaxies, they are also clustered on the sky. If you plot the directions of angular momentum on the sky, they will be, a lot of them will be concentrated around the angular momentum of, not surprisingly, the LMC. And the galaxies that are painted blue are the galaxies that are currently the LMC satellites. So it's not surprising that they have the same angular momentum. But the galaxies that are painted red are the galaxies that might be coming with LMC on the first passage, being stripped from it, and keep orbiting in the same orbital plane. So the direction of angular momentum remains more or less the same, but physically they are now separate from the LMC. And the color shade here illustrates the overall distribution of LMC debris. So the debris stripped on the first passage would be somewhere, but they would keep coherence in the space of angular momentum. So the scenario of the second passage, here again illustrating this in the orbital plane of the LMC, the contours show the density of the LMC debris, and the colors again indicate the probability of membership. The redder, the greater the probability that the galaxy came with the LMC system. And you see that some of these red galaxies are currently quite far from the LMC, like Leo 1, Leo 2. They're sitting way outside the tidal radius of the LMC because they were stripped a long time ago. But this scenario of the second passage of the LMC might be a good explanation, or at least a plausible explanation, why we have the coherent structure in the space of the galactic satellites. Although it's certainly not the only possible explanation, and it needs to be tested more rigorously in the future. And with this, I conclude. My main points to take home are that the LMC is, well, it's the biggest and most interesting troublemaker in the outer part of the Milky Way. When we examine the kinematics of anything that is beyond 20, 30 kiloparsec, we have to take into account the perturbations induced by the LMC. And very annoyingly, its past orbit is rather uncertain because its present-day position velocity are so close to the escape velocity that even small changes in the galactic potential or small changes in the assumed velocity of the LMC lead to very different past orbits. But that also could be turned around and used as a very sensitive probe of the dynamics of the Milky Way in the past. And the second passage scenario, as I said, it's possible. It's not mandated, but it's quite possible. And in this case, it will naturally explain that LMC comes with this entourage of beautiful ladies. So with this, I conclude. Thank you. Okay, to hear other people connecting on Zoom, I should probably turn on the sound to hear them. Okay. Questions from the, yes.
On the Leo 1 constraint for the mass Milky Way. So I would expect that because of the argument you're explaining that basically not really reliant to the the mass would, if you consider the effect of the LMC, which would be the mass of the Milky Way, because it's driven a lot by but it's still around 10.
Yes. Ignoring the LMC, 10 to 12 will not be able to keep up the Leo 1 bound.
So you mean it's going down?
That no. What I'm saying is that including the LMC, you have better consistency. With the Milky Way. So you can have the Milky Way mass as low as 10 to 12 and still have the Leo 1 as bound system.
Okay. Otherwise, it would be 2 or 3 times that.
Yeah. No, I don't see any. Raise hand. Okay. Yes, please unmute and ask the question.
Very interesting talk. I have a question, and that is about the the satellite plane that you talked about. And I wonder whether, so are you saying that by properly accounting for the LMC, it's kind of it's very natural to expect the satellite plane? Is that essentially the conclusion?
I would say it's more natural, yes. The caveat here is that I cannot in this formally estimate how likely is it to produce the satellite plane in the first place. It's quite natural that the debris stripped from the LMC would populate the same orbital plane. Or if you find galaxies in this orbital plane, they might be coming from the LMC. So what this analysis gives you is the conditional probability that any given galaxy comes from the LMC system, given its present-day position and velocity. And this conditional probability is around 50% for a few galaxies. So in that sense, it explains their position, but it doesn't explain the existence of the satellite plane or how likely it is in the first place, because there have been a lot of debate about the discrepancies between the predictions of cosmological simulations in lambda CDM and the existence of satellite planes. Basically, the conclusion is satellite planes are quite rare, even if you take into account situations where the galaxy might have a big neighbor like the LMC. It still doesn't make these satellite planes as prominent in most cosmological simulations. But this is, again, an ongoing debate there, and maybe we are missing something in physics. It's natural that satellites come in groups, so this group accretion might explain the satellite plane, but it do not have to come with the LMC in particular. They might be just coming with their own group. What I'm saying is that this is one possible explanation.
May I ask a follow-up question on that same topic? And that is, so how important, so if, I'm aware, of course, that people are trying to, study this in n-body simulations, which are often, just on the sense of how many halos and subhalos and what is their structure and so on. Do you think you need to have the actual modeling of the stellar component of these satellites in order to get this correct? I mean, could that be a potential explanation for the discrepancy, or do you think it's essentially sufficient just to look at the dark matter halos and subhalos?
I think this is probably a more general question, not particularly linked to the LMC interaction, because not all dark matter halos would be populated by stars. So lower mass halos will not be, yes. And that's, I think it's more general question, what's the correspondence between the stellar tracers and the underlying dark matter distribution? For the galaxies listed here, some of them are really faint, like these guys here, they might be, like most of them are ultra faint galaxies, which have a handful of stars. And quite possibly there are many other halos which are not populated by stars at all, but there is no way to detect them, at least with our technology currently.
Okay, thank you.
So in these models where people are trying to include the response of the global response of the Milky Way, are they actually including the light components consistently?
Yes, and partly yes, partly no. But for example, here these are pure n-body simulations in which everything is live, everything is responding self-consistently. You can get almost the same result by looking at the motion of two extended masses, like rigid Milky Way, rigid LMC. As I said, the Milky Way is deforming. So what I'm saying rigid is the rigid potentials, and then looking at the motion of tracer particles in these moving rigid potentials. You will get perturbations that are almost the same. Of course, now you have to account for the particles to moving and change the rigid potentials to something that is deforming. But the trajectories of test particles do not change that much. It's, again, the second order change, so to say. It might be important for some aspects. For example, for the orphan chain upstream, it has been shown that neglecting the deformations of the potential lead to some biases. But I think it's kind of next level perturbation. So you can get the basic qualitative picture even looking at rigid potentials. I think
as I was expecting, so this is a question goes back to the dynamical picture itself will be affected by the global models.
Yes, I think in that case it's slightly different because what Martin has been talking for decades about is more like a persistent, regular things. Like if a satellite has been orbiting a galaxy for several orbital periods at least, it induces some sort of global perturbation. It's not just the local wave, but it's the perturbation of the entire galaxy that keeps wobbling around. In this case, regardless of whether it's first or second passage, the current perturbations of the Milky Way halo look more or less the same. So on this picture, the difference between the first and second passage scenario are completely insignificant. You can look at it as one-time events.
Okay. Can you say something about the shape of the Milky Way? I think you probably assume spherical in some of these things.
Uh-huh.
I was wondering if you can say something, if you could measure the shape.
Mm-hmm. Yes. Okay. Yes. Well, that's a good question. Unfortunately, I deleted the slide from this talk, but from the fitting of streams, the Sagittarius stream in particular, I had actually to assume a relatively flexible model for the Milky Way, including the change in shape with radius, in order to fit all the properties of the stream. So it had to be flattened in the disk plane in the inner part, and then flattened but in a different direction in the outer part, in order to match the properties of the stream. So it has to change to some extent. But the thing is that the fits from the orphan stream, they also, those people also had flexible model for the shape, and they shape and the orientation did not quite agree. So I think there is still certainly, there is some sensitivity to the shape, but that would be mostly in the stream modeling, because streams are better suited for these delicate measurements. When you look at the dynamics of the satellites as a whole, I think there is very little hope that with the current samples we can get strong constraints on the shape.
Question for dark matter directed
Mm-hmm.
What kind of effect do you think might happen on the local dark matter? Is Lewis serum totally holds, or does the Milky Way, or does the disk gas enough to violate? I mean, make invalid Lewis serum, and also if Lewis serum.
Oh, honestly, I'm not that familiar with this thing, but I can just repeat what I said from these studies is most of the effect you would see in the high velocity tail. And of course, it will also come from a particular direction of travel of the LMC. Yeah, if your experiments are sensitive to the direction and specifically to very high velocities, then I think the signal from the LMC should be very clearly visible. Okay.
So, okay, let's thank Eugene for